Welcome back. In this video, we're going to begin talking about the intermolecular forces and where they each arise. I'm going to make one video for ion dipole, hydrogen bonding, and dipole-dipole, and then I'll make a separate video for learning the dispersion because it's a little lengthier and it's a little bit more to explain for that one. And then after that's over, we'll do a separate video where we kind of go through some practice together on how to pick out IMFs. But for now, let's focus on this slide as we introduce this topic. I wanted to remind you that there are 4 types of intermolecular forces that we're going to learn about. Most chemistry teachers say that there are only these 4, but as you go into organic chemistry, people who really start splitting hairs start identifying some even more different types of IMFs. But for you guys, for most of you, all you'll ever see are these 4. So just briefly, we have the ion dipole, which is unique because it is a mixture, or it can only occur in mixtures. And then you have the van der Waals forces that are grouped together. And then we'll talk about hydrogen bonding and dipole-dipole in this video. Well, let's start with ion dipole. It's really the easiest of the IMFs to talk about, but it seems like historically students just don't want to get it, or I don't do a good job of explaining it. So again, for ion dipole, this can only happen in a mixture. You have to have 2 components. You have to have a polar substance that's usually the solvent, such as water or such as ethanol, methanol, and alcohol, something like that. And then you have to have an ionic compound that you're dissolving in that polar solvent. What will happen is the ionic compound will dissociate, and it's going to break into its cation and its anion, as shown here by a red skittle and a green skittle. The purple jelly beans represent the solvent molecules. So again, we have a polar solvent. That's why you see positive, negative signs on each jelly bean. We know that if it's polar, there's going to be a partial positive area inside that molecule, and then there will also be a partially negative. The ion dipole force here is represented by these red dashed lines. For the cation that came off of the ionic compound, it will be attracted to the negative part of the dipole in each of the solvent molecules. So there will be an electrostatic force. Now this is only inter. This is pretty weak. This isn't the same, it's the same concept, but it's not the same magnitude as an ionic bond, because in an ionic bond, you would have a full positive charge +1 or even +2 or +3 being attracted to a full negative charge, -1, -2, -3. But here you have a full positive charge only being attracted to a fraction of a negative charge. Okay, so it only is able to form a weak intermolecular electrostatic attraction, kind of like static clinging or something like that. But the important thing here for around the red cation, I want you to notice that the molecules of the solvent are always with the negative side pointed. And then for the anion, the green skittle down here, notice that it flips. It's the positive pole of the solvent molecules that are attracted to the anion. The ion dipole force, this is actually what causes the dissociation to occur. These solvent molecules start surrounding the lattice, and they kind of attack the lattice when you drop an ionic compound, such as salt, sodium chloride, into the solvent. And they begin forming these ion dipole forces, and it works to kind of pull the ions out of the lattice. And once one of the ions starts slipping out of the lattice, it exposes more of itself. That allows like another jelly bean to come in and grab it. So eventually there's enough surrounding it to actually pull it out of the lattice. An ion dipole force is not stronger than an ionic bond, but when you team up and I get a dozen of these solvent molecules pulling on an ion, that is usually enough to add up and eventually become more powerful than the ionic bond. That's what causes anything that's soluble to be able to dissolve in water. You will recognize these because you have to be told that you're dealing with a solution. So you'll see the AQ, aqueous, a lot of the times next to an ionic compound. All right, so another very similar IMF is dipole-dipole forces. If you notice now, we only have the purple jelly beans. So this is only a pure substance, a pure solvent here, and it has to be polar. So we have to go through all that rigmarole of Lewis structure, geometry, is it symmetrical or not? If the answer is no, then we identified it as polar. Now we know anything that we identify as polar is going to have these dipole-dipole forces. These are also called permanent dipoles because these do not shift, they do not change, they are always there, and they are a result of the structure of the molecule. If you'll follow along with me in the picture here, I'll kind of try to explain what's going on. Let's focus on this middle jelly bean on the left-hand side. You'll see that it's got a positive and a negative pole. The positive pole of this jelly bean is going to be attracted to the adjacent negative. So if you'll follow the solid red lines, you'll see that it's got an attraction for a neighbor, an attraction for its neighbor to the right, an attraction for its neighbor on the bottom. At the same time, though, that positive pole will also repel the positive poles of its neighbor. So if we'll trace the dotted blue lines to show where it is repelling. You always have this mix of attractions and repulsions from these permanent dipoles. In the end, though, these molecules are going to orient themselves. They're going to spin and tumble until they get to an arrangement that minimizes the repulsions. You will always have slightly more attractions than repulsions due to the way they fit together. And they sort of do that as if they had a mind to think. But those are dipole-dipole forces. They are weaker than ion dipole because ion dipoles have at least a full charge around the ions. So according to Coulomb's law, you'll get a stronger attraction. These are all just partial charges, so according to Coulomb's law, you do not get the same magnitude of electrostatic force. Now I want to talk about hydrogen bonding. We're putting this on this particular video because hydrogen bonding is just a special case of dipole-dipole. So the most basic requirement for hydrogen bonding is that you have to have a polar substance. Okay, you have to be polar. Then another sort of requirement is you have to have hydrogen in the molecule. Why hydrogen? Well, the reason that hydrogen is important is because it's tiny. And when hydrogen forms a covalent bond, the electrons are more or less stripped away. So hydrogen becomes almost a naked proton sitting out there, which is a relatively large partial positive. So we have to be polar, we have to have hydrogens, and then the bond with hydrogen has to be extremely polar, which means fluorine, oxygen, and nitrogen are the only elements that can make this happen. They're the only ones that can make hydrogen be super polar and almost positive in this bond. So why? Why F, O, and N? Well, there are two reasons. And those reasons are that F, O, and N are all very small. And because they are small, the electrons that are being shared are closer to the nuclear charge of F, O, and N. And so it's allowed to pull harder according to Coulomb's law. A second reason is that they are the most electronegative elements, and so they pull the hardest on hydrogen's valence electrons, making it almost fully positive, but it's very polar. As a result, these hydrogen bonds, this subset of dipole-dipole, are very strong, significantly different in the effect they have on physical properties. So hydrogen bonding is very strong. All right, we'll stop here. We'll pick up in the next video talking about London dispersion.